Good evening. Sorry for that. We can begin in another 2 minutes. I am waiting for some more people to join. Okay, so let us start. Looks like not many people will be joining today. Uh, I'll share my screen. Please confirm if you can see my screen. I hope my screen is visible.
Yes, ma'am.
Okay, thank you. So, yeah. So welcome to week 5 of the tutorial session. Today we will be talking about atomic layer deposition ALD and PVD, that is physical vapor deposition. So first let us begin with a problem on ALD. So a student has to optimize an ALD recipe with precursor A and precursor B. So if you remember atomic layer deposition, we usually have at least two precursors, right? Uh, so so these are the two precursors that we have, and he or she is presents the following data. Now we have to help them to understand it. So this is the data. Now let us see what are the questions that come up on the data. So um, from run, so why did increase in temperature from run 1 to run 2 does not lead to an increase in deposition rate? Okay, so let us look at run 1 and run 2. So like any ALD recipe, in each run, first we will first we will give a dose of the precursor, then there will be some soak like so basically first we will soak the precursor A. We have two precursors. Then there will be a purge in which we will send just nitrogen that will remove the precursor A from the chamber. Then we will put precursor B, and then there will be a purge of B, again nitrogen gas that will remove B from the chamber. So that will be the process flow. So here, so run 1, the first precursor temperature they have given it as 40. uh, 40 degrees Celsius, and then the time is 2 seconds. So A will be sent in the chamber for 40 degrees at 40 degrees Celsius and for 2 seconds, and then we will have a nitrogen purge time of 3 seconds. Then the next precursor B will come for 0.4 seconds, and then the B purge time will be 9 seconds. Now another thing that they have mentioned is the substrate temperature. So ALD is happening on some substrate, right? So we are depositing first A and then the B atoms, but everything is happening on a substrate. So this substrate temperature is also given to us, that is 100 degrees Celsius. And after this entire process, what was the growth rate that was observed? So here it was observed 0.01 nanometer growth rate, and in the run 2 it was observed 0.01, again the same growth rate. So what is the difference between the two runs? If you notice, the only difference in the two runs is the substrate temperature. So substrate temperature is 100 degrees Celsius for run 1 and 150. So it's higher for run 2. So the question is, why did the increase in temperature from run 1 to run 2 does not lead to an increase in deposition rate? From the process flow we are able to see that the like for the given two runs there was no increase in growth rate that the student has observed. So why do you think that might be the case? Anyone wants to guess?
Guess is like, ma'am, that precursor temperature is same for both run.
Exactly. So precursor temperature is same, everything else is also same, uh, and the substrate temperature is not affecting it. So can you tell me why the substrate temperature is not affecting the growth? So if you remember, there was one slide in which professor had told that the growth can be a function of substrate temperature. However, when we are in the uh, so if this is my substrate temperature and this is the growth graph can look something like this or something like this. However, we usually do ALD only in these regions where it is like, so the growth is limited by the chemisorption process. So in this region it does not depend on the temperature so much. What happens is, so there will be a substrate and the A atoms will come and chemisorb on the substrate. So chemisorption is not like adsorption. So adsorption is like when we purge it, some amount of A atoms, if they have just adsorbed on the substrate, they can get desorbed again. But when we say chemisorption, it's like a strong chemical bond that forms for atom A with the substrate. Now, once all the bonds are formed, there is no more place for A to form further bonds, and A does not form bonds with A itself. So that leads to a saturation, and we usually operate in this saturation regime. So it even though if we increase the temperature, it does not affect it much. So that is the reason why increasing in the temperature from R1 to R2 does not lead to any increase in deposition rate. So because it is not leading to any increase in deposition rate, we can safely assume that we are somewhere in these temperature regimes. That is what I meant. Okay. So why is there an increase in deposition rate from run 1 to run 4? Okay, let us look at run 4 now. So here the difference is in precursor temperature. Now just like you said, when the precursor temperature has increased, we see that the growth rate has increased 4 times. So yeah, so why is the precursor temperature affecting the growth rate now? it shows that the growth rate is not actually in the self-limiting regime. So although the temperature that we found, the temperature might be in the self-limiting regime, the growth rate is still increasing. That means that um, so okay, so say this is my wafer, and I send the precursor A. Now A is adsorbing at different sites, but there are still vacant sites that are left. For otherwise, how can we increase the growth rate? Am I making sense? So uh, okay, let me try like this. The precursor temperature, uh, what does that change? So usually these precursors are in liquid form. So when I increase the precursor temperature, that just means that the vapor pressure of the precursor is increasing. When the vapor pressure of the precursor is increasing, uh, that means that the dosage of precursor that is in the chamber for the same amount of time. So here both the soak time is the same, right? So for the same amount of time there is more dose of precursor in the chamber. So what does that mean? So that means there is more A present in the chamber, and that is filling the rest of the vacant sites that were not filled in the run 1, and that is why we are getting a higher growth rate. So although the temperature was optimum in the run 1, the dose was not optimum, and just by increasing the precursor temperature he is able to get a better growth rate. I hope it makes sense. Is that okay?
Yes, ma'am.
Yeah, thank you. Uh, yeah, okay, let's move on to the next question. Why the deposition rate is different between run 3 and run 4? Okay, now what is different in run 3? They have soak time which is 1 second compared to run 4. So again the same argument applies here. The dose in a smaller soak time will be lesser compared to in a larger soak time. So um, so since we are giving lower dosage, so it has not yet reached the self-limiting stage. So then the growth rate per cycle is 0.02 nanometer, which is lesser than 0.04 nanometer per cycle. Why there is no difference in the deposition rate of run 4 and run 5? Yeah, here the difference is in the purge times. So the purge time is higher for run 5. Um, while that is not making any difference, is just that it just means that 3 seconds purge time is enough. So if you remember, the purge graph it was also like the concentration that gets purged, so the concentration that is left in the chamber is very high for shorter purge times, but as we increase the purge time, the concentration kind of gets saturated, right? So we are already in this saturated regime, that's why it might be that increasing the purge time any further is not helping us.
Ma'am, it's like that, na, that the monolayer creation is done,
Hmm.
and if you are increasing that is from 3 to 6, it is not affecting that thing like that, na?
Mm, so monolar creation is, so purge is the nitrogen purge. So when we put nitrogen, we are actually putting it to
Yes,
remove
ma'am.
the A atoms. So whether the monolayer
Extra.
is
Yes.
created or not, that regardless of that, the it is not depending on that. So regardless of that, 3 seconds purge time is enough to remove all the excess A atoms that are present in the chamber.
Yes, ma'am.
Right? Okay. Thanks. Uh, okay. So can we move ahead to next problem? Yeah, I'll move ahead. So which of the following statements regarding ALD is true? So in ALD, temperature and pressure window, precursor is designed to not adsorb on itself, coating a monolayer or less per cycle. So what they are saying is the precursor is designed so that if I have A layers, we cannot have another A layer on top of this A. So the precursor is designed to not adsorb on itself, coating a monolayer or less per cycle. So some of the bonds might be weaker, but the rest are A. So second point is growth rate strongly depends on temperature within the ALD window. So they are saying within the window where we do the ALD depositions such that we get a monolayer, the growth rate strongly depends on temperature. Third point is single component ALD for films like TA, SI, germanium is practical possible within the ALD temperature window without plasma enhancement. So basically we can have single component ALD without plasma enhancement. So which of these is true? So only one answer is true. Can you take a guess? Okay, so as we have already discussed in ALD, so the precursors are chosen such that they do not adsorb on themselves. Otherwise, we will have multiple layers, right? So we want to restrict it to a monolayer. So the precursors are basically first point is true. So in one cycle we have only a monolayer or less than a monolayer. And the rest are false. So the second one is false because growth rate does not depend on temperature in ALD window, just like I told in the previous case. So ALD window is chosen such that it is temperature independent. The growth is only limited by the chemisorption process or by the flow of precursors. It only depends on them, and it's very weak temperature dependence or no temperature dependence in ALD window. So this is definitely false. And the third point is single component ALD films like TA, SIG within the ALD temperature window without plasma enhancement. So this is not possible. Actually, for doing a single component ALD, we require plasma enhancement. How we do it is is beyond the scope of discussion, but we can actually do single component ALD. However, we will require plasma enhancement. So this is also false. Okay, so next question is on sputtering. So instead of normal sputtering, we are going to study the sputtering of alloys. So alloys are made up of more than one material. So here it is a two component alloy. So as we discussed in class, it is possible to deposit thin films of alloys using sputtering, something not possible with evaporation. Right. So with evaporation we cannot deposit alloys because the different components of the alloy will have different melting temperature, different it will start to evaporate at different temperatures. So so because of that, so the sublimation temperatures will be different. So because of that we cannot use evaporation for getting a reliable composition of alloy deposited on our film. So that's why people prefer sputtering. But then how is sputtering able to achieve the composition that we desire? So on the face of it this is unintuitive because different materials have different sputtering yields. So uh, so if I am using argon gas for argon plasma for sputtering, one argon atom might easily knock off some A atom, but might not that easily knock off the B atom. So so then again, how do I ensure that my composition of so if my target composition is some AX B1 minus X, how do I make sure that the deposited film also has the same composition? So some argon ions plasma will be bombarded on this target. So this is the target, and then the atoms that are knocked off from the target, so A atoms, B atoms, they will move and deposit on the substrate. So then how do I ensure that the composition of the thin film that is deposited is same as the composition of the target? So yeah, so this assignment will delve into the details of wherever intuition is leading us astray. Okay, let us start with a sputtering target of binary alloy AX B1 minus X. Assume the number of surface atoms per centimeter square are n. So, uh, the target here. So, suppose that this is the sputtering chamber. This is the target and this is the substrate. So, the target here is consists of AX B1 minus X alloy, and so the target has some surface atoms, right? So, the number of surface atoms that are present are n. So, out of this n atoms, the concentration of A atoms at the start is Na naught. So, Na denotes the concentration of A atoms, and since we are for time t equal to 0, I will write it as Na naught. That is nothing but x times n, because x is the ratio of A atoms and n is the total number of atoms, and Nb naught is 1 minus x times n. Now, suppose the sputtering is being done using an argon gas, Rg of which are impinging the target per centimeter square per second. So, this is the impingement rate. So, Rg tells us the number of atoms of argon impinging the target per centimeter square per second. So, rate of impingement. So, that is Rg. So, suppose the sputtering yields of A and B are Ya and Yb. So, say an argon hits A, the probability of A being knocked off is Ya and probability of B being knocked off is Yb, and we are saying that Ya is greater than Yb. So, the first question is, at the start, what is the probability that an impinging argon atom will strike an atom of A in the alloy target? What is the probability of it striking an atom of B in the alloy target? So, this is very easy. Someone wants to take a guess? So, there are xn, I will just write down the answer. So, there are xn number of A atoms and total number of atoms are n. So, xn by n is nothing but x. So, x is the probability of striking A. Similarly, can you tell me the probability of striking B? It will be 1 minus x. So, basically the probabilities will be equal to the ratio of A and ratio of B. So, like if there are xn by xn number of A atoms on the surface and n is the total number of atoms on the surface, then the probability of striking A will be xn by n, like that. So, let us move on. At the start, how many atoms of A and B leave the surface per centimeter square per second? Let us call this number sputtering rate, phi A naught and phi B naught. So, what will be phi A naught? Phi A naught is number of atoms of A leaving the surface per centimeter square per second. So let us see what and all they have given us. They have given us the concentration of A atoms at the start on the surface, and they have given us the sputtering yields, right. So from this can we get uh, the number of so the rate of sputtering. Also one more thing, this is the impinging rate, that will also play a role. So just by intuitively thinking, do you want to take a guess? Okay, if not, first of all let us write down the concentration of A atoms on the surface. So that will be n is the total number of atoms times x upon n. So or what I can just write this as x. So x times ya times rg. So this is the impinging rate. So what is the probability of an argon atom hitting the uh, hitting hitting the surface? Then in times the probability of the argon atom hitting the A molecule times times the yield of A. So so when argon is coming, first of all what is the probability of argon hitting the surface? So that is given by this Rg. Secondly, if it is hitting, is it hitting the A atom or the B atom? So the probability of it hitting A is given by x. And thirdly, if it has hit an A atom, what is the probability that the A will get sputtered? So that is given by the yield Ya. So uh, that is what is the sputtering rate that we require. So similarly, what will be phi b? Phi b will be 1 minus x times Yb times Rg, right? Okay. At the start, what is the total number of atoms that are sputtered away from the target per centimeter square per second? Again, they are asking a sputter rate, but the sputter rate for total number of atoms. So that will be the sputter rate for A plus the sputter rate for B, right? So until now everything is fine. Lot of symbols, but all we have done is we have found out what is the rate of uh, so initially at the start what is the rate of sputtering of A, sputtering of B and the total sputtering. So yeah, so that depends on the probability of hitting A atom times probability of knocking A off times the probability of argon hitting the surface, and similarly for the B atom, and then we just added it to find the total probability per centimeter square per second of sputtering. So yeah, so total number of atoms sputtered away per centimeter square per second. So, assuming the stiction coefficient is no different of A and B, what should be the composition of the thin layer deposited on the substrate? That is, if the material deposited is AY, B 1 minus Y, then what is Y? So, now we till here we just found out like how much of A and B has got sputtered, but once it has got sputtered, it has to go up and deposit to form a film. So, in this deposited film, say the composition turns out to be AY, B 1 minus Y. So, then what is this Y? Is it the same as X or different from X? So, basically we have to find the fraction of A and the fraction of B that is getting deposited. So, the fraction of A atoms deposited will be nothing but Y, and so the fraction of A atoms deposited will be nothing but the fraction of A atoms that have got sputtered upon total number of uh, A and B atoms that have got sputtered. So, that will be X. So, that will be basically phi A naught upon phi total naught. Agreed? This will be nothing but XYA RG upon XYA RG plus 1 minus X YB RG. This RG we can remove from all the terms, and that leaves us with XYA upon XYA plus 1 minus X YB. Okay, so this is the ratio that I am getting. So, earlier AX B 1 minus X was there. Now we have, so this was there in the target. Now we have deposited AY B 1 minus Y, where this Y depends on X in the following manner. So, this Y is nothing but X times some number, what is the number? YA upon XYA plus 1 minus X YB. Okay. So, then this is not desirable, right? We do not want this to happen. So, so the answer to these questions is the basis of our intuition. So, we intuitively also thought why sputtering will give exactly X B 1 minus X when the yields for different yields are different for A and B, right. So, so still why sputtering is used for this. So, at the start of sputtering, composition of the deposited film will indeed be different from X, but let us continue and see the evolution of the surface concentration of A, that is Na. So, Na is the surface concentration on the target, and surface concentration of B, that is Nb, surface concentration of B on the target as a function of time. Okay. So, suppose we let this continue for a small time delta t. So, for a small time delta t, we are sputtering the target and depositing on the substrate. So, delta t is so small that only a fraction of the top molar layer of the target gets removed. During this time, some atoms of A and some atoms of B have left the surface. How many atoms of A and B per centimeter square have left the surface? So, the number of atoms that leave the surface will be the sputtering rate into the time, right. So, we know that the sputtering rate is phi A naught into delta t. and we had determined this phi a naught in the last question. That came out to be x y a rg into delta t. Similarly, for how many atoms of B per centimeter square that have left the surface? Number of atoms of B per centimeter square will be phi B naught into delta T, that will be equal to 1 minus x y B g delta T. Okay. So now if so many atoms have left the surface, how many atoms of A and B are left on the surface? So initially how many atoms of A were there on the surface? Let me just write down number of atoms of A left on surface. So that will be initially how many were there minus how many left. So initially there were total n number of atoms on the surface, and x was the fraction of A atom. So nx were the total number of A atoms on the surface. So if nx is the total number of A atoms, now how many are left? So that will be nx minus x times Ya Rg delta T. But that is not all, right. So when some atoms are leaving the surface, the layer beneath the top layer is getting exposed. So there will be some A atoms on that layer as well. So we need to take into account those also. So right. So there will be some places where the top layer is gone. So there will be some A atoms that are exposed. How do we find out uh, how many A atoms will be there? So in the previous question we found out phi total, right. So phi total is nothing but phi total naught is nothing but the rate of sputtering of total, like rate of sputtering of both A and B included. So this times delta T is the rate of sputtering of total number of atoms. So this is the total number of atoms that have already left, and x fraction of them will be A. So here I can write plus x phi total naught times delta T. Is this correct? So similarly also we can find the number of atoms of B left on the surface, and that will be nothing but, so what is the total number of B that were initially present on the surface? N times 1 minus x. Then number of B atoms that left the surface, again 1 minus x times YB Rg delta T, and the number of B atoms that have reappeared from the layer beneath the top layer. So now that will also be considered as the top layer, right, wherever it is exposed. So that will be 1 minus x times phi total naught delta T. So now we know how many A and B atoms have left the surface and how many atoms of A and B are left on the surface. So now the surface composition of the target has changed. So initially the target had Ax B1 minus x as the composition. Now the surface composition of the target will be it will be not x, basically it will be something different. So that will be given by A, this thing divided by total, B again this second part divided by total. So has the relative concentration on the top monolayer changed because of sputtering? If it has, what is the new ratio of A is to B on the surface? So basically they are just asking us A is to B, and that is nothing but this term is to the, this is to this. So for that I will just take the x outside, x times n minus ya rg delta t plus so now the new ratio has changed. Earlier it was x is to 1 minus x, now it is something more complicated. So x is to 1 minus x is still there, but there are some other terms that are also coming up. So if you look at it, the only two different terms are these two, right? So yeah, so among A and B, whose concentration has increased and whose concentration has decreased? So, um so in the question it was given that YA is greater than YB. So using this we have to answer this question. So if YA is greater than YB, this implies that YA Rg delta T is greater than YB Rg delta T. So what does that mean? So that means that minus of YA Rg delta T is less than this. So this top term is lesser than the denominator. So basically that means that A is to B has decreased. So now uh, the ratio of A is to B has decreased. That means the number of A atoms have gone down compared to the number of B atoms. Now if you think about it intuitively, that makes sense, right? So I have a wafer and I am sputtering it, and the yield of sputtering is higher for A compared to B. So then more number of A atoms would get sputtered away compared to the B atoms. So in that case there will be more B that will get accumulated on the surface when compared to A. So then the A is to B ratio will decrease. So in now what they are asking is in the next delta T. So now with a different composition of the target, we have to find the same things. So in the next delta T, how many atoms of A and B will leave the surface per centimeter square per second? So again they are asking us the same phi A, but this is after the time delta T. That will be nothing but Na Ya Rg. So now the Na has modified. So the surface concentration has changed, and the surface concentration has become, uh, if you look here, it is x times some big number. So I will just write it down. Earlier it was just x, right? Now it is x times n minus plus the term coming from the layer beneath. and then YA into RG upon, okay, no upon, we are just writing the phi A delta T. Next let us write phi B. It will be NB YB G, that is nothing but 1 minus x times n minus YB RG delta T plus phi total delta T into YB RG. So we have to so this is the new phi A and phi B. So we have to compare this to phi A naught and phi B naught. What were phi A naught and phi B naught? Phi A naught was just x YA RG, phi B naught was just 1 minus x YB RG. So this is the extra term that is coming up. Right. So has the relative sputtering rate of A and B changed? So yes, it has changed. So the relative sputtering rate, so from looking at this we cannot get the relative sputtering rate. Relative sputtering rate is probably just phi A naught um, upon phi A. Where is it? Basically just phi A upon phi A plus phi B, that will be the relative phi A. So has it changed from time t equal to 0 to time 0 plus delta t? So obviously it has changed. So which one has increased and which one has decreased? So just from the previous question we see that n minus YA RG delta t is less than n minus YB RG delta t. So basically it means that phi A delta t has decreased whereas phi B delta t has increased. So even though YA is higher, but relatively from relative to the previous case, the phi A in this case would have reduced. So just like I said here, because the number of A atoms on the surface has gone down, because this term is going down, right, because the Na is going down, because of that the phi A like phi A will also go down compared to phi B, since the B atoms get accumulated on the surface. So there will be more sputtering of the B atoms, and because of that NB has increased, because of which phi B delta T will increase. So which has increased? Sputtering of B, sputtering of B atoms has increased, and which has decreased? So A atoms have decreased. Sputtering rate of A atoms has decreased. So are you following until now? Like you can ask if there is anything that you want me to repeat, or because there is a lot of things going on. Okay, in that case I'll move forward. Um, right, yeah. If you have been following the question correctly, you will see a trend. The different sputtering yields change the surface concentration of the target. So yeah, I'll just read it. So why they are saying different sputtering yields is just because YA is different from YB, and they are telling Y is greater than YB, right. So the sputtering yields are different. So the different sputtering yields change the surface concentration of the target, which changes the relative sputtering rates, which changes the relative surface concentrations of A and B, which once again changes the sputtering rates. So because the yield of sputtering for A is higher than yield for sputtering for B, then A concentration on the surface will increase, and because of the increased surface concentration, again the sputtering rate for A will increase. Will decrease, because sorry, what did I say? So because YA is greater than YB, that means that the sputtering rate of A is higher than sputtering rate of B. So because the sputtering rate of A is higher than sputtering rate of B, more amount of A atoms will be sputtered. So the surface concentration will readjust so that there is more B on the surface compared to A. Then the sputtering rate of B will go on increasing, will increase, and this will go on until we reach some steady state. So ultimately the system will stabilize. Before proceeding forward, take a moment here and try to guess where the system will stabilize. So for the system to stabilize, what should happen? The number of A atoms leaving the surface should be the same as the number of A atoms that are emerging from the layer beneath the surface layer. So just beneath the surface layer. So whenever the atoms leaving is equal to the atoms which are getting uncovered, at that time for those surface concentrations we will have a steady state. So right. So yeah. So let me just write down the number of A atoms leaving. That will be nothing but the rate of sputtering of A atoms into delta T, that is the time. And for how many number of A atoms will get uncovered? So this is the component that is coming from the layer beneath. So that will be nothing but the total sputtering rate times delta T. So how much ever atoms from the top layer have gone or got sputtered away, times X, because X is the fraction of A atoms in the bulk. Right. So for steady state, I'll just write it here. For steady state, I need the ratio of A is to B, that is leaving my surface, to be equal to the ratio of A is to B, that is getting uncovered. Right. Only then I will have a steady state. Otherwise, there will always be some amount of A increasing on the surface or B increasing on the surface, or some accumulation that will be there. So yeah. So let us equate these two. So A leaving the surface is nothing but phi A delta T. Similarly, B leaving the surface is phi B delta T. A uncovered is phi total delta T times X, and B uncovered is phi total delta T times 1 minus X. So what does that mean? So that means that phi A upon phi B should be equal to X upon 1 minus X. So this should be the ratio of the sputtering rates. Only then we reach the steady state. So yeah, so this question got in a wrong order. So suppose I told you that the system will stabilize when the ratio of sputtering rate of A and B becomes X upon 1 minus X. We just saw why that is the case. What will the ratio of surface concentration A and B be at that point? So we know that phi A upon phi B should be equal to X upon 1 minus X, so that we reach steady state. So what is the ratio of surface concentrations? So they are asking us Na upon Nb. So what will be Na upon Nb? So let me just write down phi A upon phi B first. Phi A upon phi B is nothing but Na, so not actually Na by N. So Na by N, so Na naught by N was x initially, right? So Na by N into by A. So this is nothing but the probability of um, when argon is hitting the substrate, what is the probability that the A atom will be hit? That is this probability. So now this has to be equal to x by 1 minus x. So from this, can we find out the ratio of Na by Nb? Simple, right? We just cancel these terms out. So Na by Nb is nothing but Yb times x upon Ya times 1 minus x. Right? So from this, what do we see? So at steady state, uh, the concentration of A atoms is inversely proportional to the yield of A. So if the yield of A is high, then the concentration of A atoms on the surface will be low. Okay. Similarly, the concentration of surface concentration of A atoms is directly proportional um, to the fraction of A atoms that I want in the film, or the the ratio in the bulk alloy basically. So we want a film of composition AX B1 minus X, right. So the number of A atoms will be directly proportional to this X. So this is intuitive, right. So if I want AX B1 minus X, um, the target the surface of the target should the number of A atoms on the surface of the target should be proportional to X. Similarly, the number of A atoms should be inversely proportional to what is the sputtering rate of A. Higher the sputtering rate, more A atoms will get sputtered. So we don't want more, we want optimum. So yeah. So if you just think about this for 2 minutes, you will understand that this actually makes intuitive sense. Okay, I'll move ahead. Yeah. So this was the rough calculations that we did, but to actually get Na and Nb, so the surface concentrations of A and B as a function of time, we need to write down some differential equations and solve them so that we get it at every time step. So let us first try to frame these differential equations. So how do we go about framing the differential equations? Yes, Vinayak, can you please unmute yourself and
I
yeah.
just wanted to know, is there a way to get these solutions for those problems you're explaining? I mean, will you be sharing some content with us?
If you want, I can surely share with you in particular. I have no access to the NPTEL portal as such. So if you send me your email address, I can share with you.
Okay,
Yeah,
can I have your email ID?
yeah, you can. I'll just put it in the. Just a minute. I'll put it in the chat box.
Okay,
You
so
can drop me
whatever
an
you,
email. I'll send you the solutions.
so whatever you are explaining, along with the solution, the content will be there.
So these are basically, so when I did the course, these were the assignments. I have solutions to those assignments. I can send you.
Okay, okay,
I can
fine.
send you the
Thank
entire
you.
assignment. There might be more questions in it also. There are more
Okay,
questions
okay,
actually.
okay. Thank you.
Yeah, no problem. Just drop me a mail because I don't have everyone's email addresses.
Yes, yes, I will share an email to you.
Thanks. All right. Right. So we were writing the differential equation. Uh, yeah. So how do we go about writing the differential equation for Na and Nb? So first, let us write down the number of A and B atoms leaving the target in dt time. So, so this will be nothing but phi A dt and phi B dt. And then what will be the number of A and B targets that are added? So why am I doing this? I want to finally write down dNa by dt, right? So to find out this dNa, I am writing the number of A atoms that left and the number of A atoms that were added to the target. So by added I mean that that were uncovered because of the top layer getting sputtered. So I just wanted to mention that these questions are not my questions. Like so, Shubhan sir has given these questions. Even the solutions are partly mine, but otherwise, yeah. So the items added to the target will be um, just like we discussed previously, phi total times dt times x is the probability of A or the fraction of A. Similarly for B, so from these two things, what will be dNa? So that is the change in the surface concentration of A atoms. Will be x phi total dt, that is the number of A atoms that were added minus the number of A atoms that were removed or sputtered, right. Now this phi total is nothing but phi A plus phi B. So I can write this as x times phi A dt minus plus x times phi B dt minus phi A dt. Right, till here I think it is fine. So from this, so this is nothing but dNa. From this I can write dNa by dt, that will be x times Rg, basically just bringing this dt down. right, and then we can substitute for phi b and phi a to get x rg, that is impingent ray, by b and b upon n. So yeah, so phi b is nothing but rg yb nb upon n minus 1 minus x, phi a is nothing but rg ya and a upon n. So then I have got dNA by dt in terms of nb and na, or you can say in terms of phi b and phi a also. Similarly, we can also get dNb by dt. So you can try it out. Basically the same procedure will follow. Instead of so what will be the atoms, so that will be basically 1 minus x phi total dt minus phi b dt. So if we just rearrange that, and like substitute for phi total, we will get 1 minus x phi a dt minus x phi b dt. So this is nothing but the same thing, just negative of this, right. So dNb by dt is nothing but, so this dt is not there because I have already brought the dt down. Just a minute. It's nothing but minus of dNA by dt. So yeah, so we have got the differential equations. Now what remains is to solve them. To solve these differential equations, we can use MATLAB and some numerical methods in MATLAB. So yeah, so since they are implicit in nature, like we have Na even on the right hand side, so because of that it's not very trivial to solve it. We can use some algorithms like ODE45 or some inbuilt functions in MATLAB to get the answers. So the solution to the differential equation, I am just showing it directly here, and this solution is for r equal to 10 power 13, Ya is 4, Yb is 1. The total number of surface atoms is 10 power 15, and x, that is, this is 0.6. So the alloy that we are depositing is of this form. So for such a condition, we see that the solution first, it like in the initial stages it is not reached the steady state, but as the time goes about 200 seconds, we see that it is almost in a steady state form. So yeah, so initially the first few layers that will be deposited might not be very, the alloy might not be just A 0.6, B 0.4 that we expect, but it will be something different. But at the later stage, when it has reached the steady state, it should be the same. So how do we verify if it is the same? So first from the, so here we had found out, right, what should be the steady state ratio, ratio of surface concentration, that should be Yb upon Ya into x upon 1 minus x. So Na by Nb should be equal to Yb upon Ya into x upon 1 minus x, right. So let us just substitute these numbers and check if what we are getting here is the same as what we expect. So Yb by Ya is nothing but 1 by 4 times 0.6 upon 0.4. If we just do this, we will get 0.375. Now in order to check this, we just need to do 0. So green is Nb, okay. So red is Na. So 0.2727 divided by 0.7273. if we do this, we again get it something close to 0.375. So that means that this graph is just like we expect, and the final surface concentrations are basically just like we expect from the alloy, even though initially there is some discrepancy, but finally we reach the same. So that's why we can say that sputtering can help us deposit alloys, unlike evaporation. So what is the problem with evaporation? In evaporation, when we are at a higher temperature, right? So whenever we are at a higher temperature, even though from the top, um, say A starts evaporating first, so there will be more A that gets evaporated from the surface. Then we will expect that there will be more B on the surface left, but that is not the case, because we are at a higher temperature. The alloy will adjust such that the A atoms from the interior will diffuse towards the surface. So then then the evaporation mechanism is not just a surface mechanism, but it becomes a bulk mechanism. But in case of sputtering is not done at higher temperatures. So there is no way that the alloy will adjust itself, or the A atoms from the interior will diffuse to the surface. So because of that it's remains just a surface phenomena, and that will limit the number of A atoms on the surface, and that will make sure that the steady state concentrations that we get are the ones that are of the target. So yeah, that's it for today. uh, if you have any doubts, you can ask. Also, any suggestions for the next class? Or so today I could not prepare much, so it got over quite fast. Yeah, yes, you can speak up, Vinayak, right?
This you have this current assignment problems like previous week and all. Will you be able to solve those or provide any solutions to that?
So previous week problems.
Yeah, like week 4 or week 3, like the current, you have some problems, right? Will you be able to solve those or give an insight into it?
Sure, I can wait. I can come prepared for those in the next
Yeah,
class
because
probably,
this
because
is the first time I have attended this session. Last 4 weeks I was unable to do it.
oh, okay, I see. In that case, you can also check the YouTube videos. If you
Okay, okay,
Yeah, yeah. But I have not discussed any quiz questions as such. If you want, I
okay,
can like I have answers only to the quizzes that have got over. Actually, I don't have answers to the recent quiz.
okay, okay.
So yeah, I'll prepare those and come for the next session.
All right, all right.
Yeah, thank you. Okay, then in that case, we can close the session today.
Okay, thank you.
Thank you, ma'am. Thank you, sir.